So I'll just take a screenshot and I will be taking help of Gemini with for my syllabus. Since I just want to understand the topics, I'll just write this prompt. Okay, so we are starting with Unit 1 Introduction. The software crisis and myth. Back in the day, people thought writing code was easy. They ended up with massive delays, broken budgets, and software that did not work. The software crisis. A common myth is if we fall behind schedule, we can just add more programmers to catch up. Spoiler, it actually makes things slower because they spend all their time talking instead of coding. The second point is what is an SDLC? It stands for Software Development Lifecycle. It's just the step-by-step game plan you choose to build your project. The models, the SDLC models are first the waterfall model. Do everything in strict order. Plan, design, code, test. You can't go back to a previous step. Like building a house, you can't easily change the basement layout once the roof is on. Okay, that's the waterfall model. It follows a strict order: plan, design, code, and test. Then we have incremental model. Build it piece by piece. First, build a studio apartment. Next, add a kitchen. Then add a balcony. Okay, that's the incremental model. Then we have prototype model. Build a quick, cheap, rough draft first just to show the client and get feedback, like a cardboard model of a house. Okay, now we have spiral model, a heavily cautious approach. You build a little bit, check for massive risks, fix them, then repeat the loop. It's excellent for expensive high risk projects. Okay, so if we want to reduce risk, then spiral model is the one we should choose. Then agile model, the modern favorite. You work in fast 2 to 3 week bursts, sprints, adapting constantly to changes rather than following a rigid plan. So as the name suggests, agile, it works in sprints, adapting constantly to changes. Then Unit 2 has modeling. This is the planning phase where we sit down with the client, sketch the layout and plan where the pipes and wires go. Requirements engineering and SRS. This is just a fancy way of saying find out exactly what the user wants. Okay? You sit down, interview them, and write down everything in a master contract called the SRS, Software Requirement Specification. The analogy is quite good here. DFD, data flow diagram, a visual map showing how data enters your system, where it gets processed, and where it gets saved, like tracking how water flows from the main supply through the water filter and out the tap. Okay, data flow diagram. Use case modeling. Simple diagram showing who uses the app and what they are trying to do. Example, customer logs in, buys item. Who uses the app and what they are trying to do. Okay, so the customer here is the who, and what they are trying to do is logs in and buys item, belongs to what they are trying to do. Coupling and cohesion. So here it says crucial exam topic. So cohesion means keep it high. We should like cohesion should be high. How focused a single piece of code is. You want a piece of code to do one thing exceptionally well, like a toaster that only toasts. Alright. Then coupling. Keep it low. How dependent different pieces of code are on each other. If changing the code for your app's dark mode accidentally breaks the payment system, your coupling is too high. You want components to be independent. Alright, so cohesion is basically do one thing well, and coupling is coupling should be low, as in one piece of code should not be related to another piece of code that does a different function, that performs a different function. Then we have refactoring, cleaning up messy code underneath without changing how it works on the outside. That's refactoring. Then we have Unit 3, quality management. This is the inspection phase. Before anyone moves in, you check if the lights turn on and smash the walls to see if they hold up. Okay. So firstly we have got the 3-box testing techniques. First is black box testing without looking at the internal code. You just type an input and check if output is right, like pressing the gas pedal to see if the car accelerates without looking at the engine. Okay, that makes sense. That is black box testing. White box testing. Testing with full knowledge of the internal code. You look at the logic, the loops, and line by line execution. Alright. And grey box testing. A mix of both. You have partial look at the internal structure to build better tests. That's grey box testing. Levels of testing. We have unit testing. Testing one tiny piece of code, like checking if a single brick is solid. And then we have got integration testing, putting two pieces together to see if they play nice, checking if the pipe fits into the sink. Then we have got system testing, testing the entire app as a whole package. Then we have regression testing, testing the app again after a change to make sure the new update didn't secretly break an old feature. Then we have automation tools. Instead of clicking manually 5,000 times, you write scripts using tools like Selenium. For testing web browsers, or JUnit for testing Java code blocks to do it automatically. Okay. I think I will have to read, understand automation tools better. I don't understand it well. I'll just start with levels of testing once again. Unit testing, testing one tiny piece of code. Okay, understood. Integration testing, putting two pieces together to see if they play nice. That's also fine. System testing, testing the entire app as a whole package. Alright. Regression testing, testing the app again after a change to make sure the new update didn't secretly break an old feature. That's regression testing. Okay. Levels of testing is fine. Unit testing, integration testing, system testing, regression testing. I'll take a look at automation tools. Let's start with Unit 4, Managing Software Projects. This is the business side. Managing budgets, dealing with unexpected disasters, and keeping the house standing years later. Okay, cost estimation and COCOMO. Before starting, you must tell the client how much it will cost. COCOMO, constructive cost model, is a classic mathematical formula that takes the estimated size of your software lines of code and calculates exactly how many months and how many developers you will need. Okay. So COCOMO is quite the tool to use. Then we have got risk and configuration management. Risk, planning for what could go wrong. What if our lead developer quits? And configuration, tracking different versions of your files so team members don't accidentally override each other's work. Tracking different versions of your files. Alright. Okay, then we have got software maintenance. Software isn't done when it ships. You have to fix new bugs, optimize performance, or add features as the years go on. Then optimize performance or add. Okay, that's software maintenance. Then we've got reverse engineering and re-engineering. Reverse engineering, taking an existing finished app and breaking it down backwards to figure out how it works. Backwards, okay, that's reverse engineering, it makes sense. Then re-engineering, taking an old clunky outdated system, breaking it down, updating it with modern tech and rebuilding it better. Okay, that also makes sense. So I was stuck on automation tools. When we talk about software engineering, automation tools are software programs designed to perform repetitive, time-consuming tasks without human intervention. To understand why they are so important, imagine you are a quality tester who just built a massive e-commerce app. Before every launch, you need to test the login page with 100 different usernames, add 50 different items to a cart, and try 10 different credit cards. Doing this manually by clicking and typing would take hours and invite human error. Automation tools lets you write a single script that does all of that in seconds. Okay. Key categories of automation tools. According to your syllabus, automation tools are divided based on what they are testing and how they do it. The first would be code level automation, unit testing. These tools test individual functions or blocks of code right after a developer writes them. They ensure the foundational building blocks work before anything else is built. Okay, unit testing. The go-to tool, JUnit for Java. How it works: if a developer writes a function to calculate a discount, they write a quick JUnit test script. If input is $100 and discount is 10%, ensure output equals $90. Every time the code changes, JUnit runs in the background to double check the math instantly. Browser and UI automation, functional testing. These tools interact with the actual user interface just like a real human would. Clicking buttons, typing text, and navigating menus, the go-to tool, Selenium. How it works. You write a script in Selenium that says, open Chrome, go to amazon.com, type laptop in the search bar, click search, verify that results appear. Selenium physically opens a browser window and executes these steps at lightning speed. Web application and security testing. These tools scan entire web networks, APIs, and databases to look for vulnerabilities, slow loading times, or crashes under heavy user traffic. What they check? They simulate thousands of virtual users hitting a website at the exact same time, load testing, or check if malicious code can be injected into a login form, penetration testing. Okay. Manual versus automatic testing, the balance. While automation is incredibly powerful, it does not completely replace human testing. Software teams use a strategic mix of both. Feature manual testing, automated testing. Speed slow, limited by human clicking and typing. Extremely fast, runs hundreds of tests in seconds. Setup cost low, you just need a person to start testing. High, requires time and skill coding to write the test scripts. Best used for exploratory testing, looking around for unexpected bugs, and user experience UX testing, checking if it looks pretty. Regression testing, running the exact same repetitive tests over and over to ensure new updates didn't break old feature. Unexpected bugs. Okay. How it fits your okay. In Unit 3, Quality Management, you'll learn that automation tools are the backbone of modern development frameworks like DevOps and CI/CD. Continuous integration, continuous deployment. Instead of waiting until the entire project is finished to test it, modern teams set up pipelines where every single time a programmer pushes new code, tools like JUnit and Selenium automatically run in the cloud. If a test fails, the code is rejected instantly, ensuring software remains bug-free at every stage. Alright. So, what should I do next? Okay, so basically I want to cover each and every part of the syllabus well, and what should I write down? Definition and importance of software engineering. Then we have software crisis and myths, software process framework. I think in Unit 1 I am not well versed with software process framework, so I'll start with that. Okay, so think of a software process framework as the skeleton of a recipe book. It doesn't tell you exactly what dish you are cooking, whether you are making a simple mobile game or a massive banking app, but it provides the essential foundational steps that every successful project must go through. Okay, the uh, the five core framework activities. Every standard software process framework is built on five core activities, no matter which SDLC models you choose, waterfall, agile, or spiral. You will always perform these five steps in some shape or form. Communication, planning, modeling, construction, deployment. Communication, talking. Before writing a single line of code, you have to talk to the client and stakeholders. Goal, understand what problem they are trying to solve, and what features they want. Then planning, mapping. Uh, this is where the project management side kicks in. Your team creates a roadmap. Goal is to define the task, identify potential risks, allocate resources, and create a timeline. Schedule, modeling, designing. This aligns directly with Unit 2 of your syllabus. It creates how the data flow and how the software will be structured structurally before the coding begins. Fourth is construction, building and checking. This is the heavy lifting uh, phase where the actual technical work happens. Goal is that the developers write the code and the testers immediately follow up with testing using the manual or automated tools like JUnit, Selenium from Unit 3 to find and fix bugs. Fifth is deployment, delivery. Software is complete and ready for the world. Goal, you deliver the final product to the customer and get their feedback and prepare for long-term support and software maintenance from Unit 4. Umbrella activities, the background process. While the five core activities happen one after another or in cycles, there are certain tasks that never stop running from day one until the project ends. In software engineering, these are called umbrella activities because they shield the project throughout its entire life cycle. Software project tracking and control, constantly checking if the team is on schedule and within budget. Risk management, keeping an eye out for potential disasters, losing a key developer or changing requirements and minimizing their impact. Software quality assurance, SQA, conducting reviews and audits to ensure the team is building the software correctly and maintaining high standards. Formal technical reviews, FTR, developers sitting down together to check each other's work and catch design errors early. Software Configuration Management, SCM, managing changes to code, document, and versions so nobody accidentally overrides someone else's work. Okay, summary. It is a structural foundation that organizes software development into core activities. and umbrella activities. I'm not able to connect the dots yet, but I will move on to a different topic. Uh, okay, Unit 2, I'll come back to Unit 2 later. And Unit 3, I think I understood most of the things. Software testing fundamentals, I'll start with that. Okay, in casual conversation, we use these words interchangeably: bug, error, fault, and failure. This is the first topic. But in software engineering, they follow a very specific chain reaction. Error, a human mistake made by a developer while writing code, typing a plus sign instead of a minus sign. Fault or bug, the actual flaw in the source code caused by that error. It sits silently in the code. Failure, when that flawed code is executed by a user and the software behaves incorrectly or crashes. An error leads to a fault, which ultimately manifests a failure. Okay. Core principles of software engineering. Before you write a single test script, you have to understand the fundamental laws that govern testing. Testing shows the presence of defects, not their absence. Testing can prove that bugs exist, but no matter how many tests you passed, you can never mathematically prove that a program has zero bugs. Exhaustive testing is impossible. You cannot test every single combination of inputs, data paths, and user scenarios. For example, if an input box takes 10-digit phone number, testing all 10 billion combination would take years. Instead, you focus on high-risk areas. Okay, early testing. Testing should start as early as possible in the SDLC, even during the planning modeling phases of Unit 2. Finding a bug in a design sketch costs pennies. Finding it after the software is deployed costs a fortune. Early testing. Then we have defect clustering. In most applications, about 80% of the bugs are hidden within 20% of the code modules. If you find a bug in a specific section, like the payment gateway, look closer. There are likely more bugs hiding next to it. So the core principles are: testing shows the presence of defects, not their absence. Then we have exhausting testing is impossible, early testing, and defect clustering. The two fundamental approaches, V and V. Software testing is split into two massive pillars, collectively known as verification and validation. Uh, Software testing, verification. Are we building the product right? Done before code runs, reviews, walkthroughs, and inspections. Validation. Are we building the right product? Done after the code runs, executing test cases, stress testing. Okay, that's the basic difference between verification and validation. Are we building the product right? This is verification. You check your work without actually running the program. This involves sitting down with your team to review the requirements documents, SRS, reading over the source code line by line, and checking design models to spot logical flaws early. Then we have validation, dynamic testing. The question, are we building the right product? How it works. This is hands-on testing where you actually execute the software code, input data, and see if the output matches what the customer requested. This is where your black box, white box, and automated testing tools come into play. The testing psychology. A great developer writes code to make it work. A great tester writes test cases specifically designed to make the code fail. Alright. Good testing requires a highly creative, destructive mindset where you ask yourself, what is the weirdest, most unexpected thing a user could click right now to break this app? Would you like? Okay. Uh, Software testing fundamentals. I'll just go through it once again. We had the terminology, error, bug, and failure. Then we had the core principle of software testing. Then the two fundamental approaches, V&V, verification and validation. Alright. Then I'd like to go to Unit 4. Which one should I start with? Unit 2 and Unit 4, I'll like to do it together. So okay, so phase 1 is the initial estimate. Before you can model or design a system, you need to, a client will ask, how much will this cost and how long will it take? You can't just guess, you use software cost estimation. Software cost estimation. This was, okay, COCOMO model. The COCOMO model. This is a mathematical formula where you input your best guesses of the project size measured in thousands of lines of code or KLOC. The formula spits out how many developers you need to hire and how many months the project will take. Then we have FPA, function point analysis, another way to measure size based on features. Example, how many inputs, outputs, and databases the app has, rather than raw lines of code. Is FPA model. Okay. Phase 2, drawing the blueprints. Once the budget is approved in Unit 4, you move into Unit 2 to figure out how to build it. You gather the requirements and document them in an SRS, software requirement specification. Then you start modeling. DFD, data flow diagram. You map out how data travels through your app. Use case diagram. You map out who the users are and what actions they take. Phase 3, structural engineering. Now you design the code structure. This is where you must balance two incredibly critical concepts that every software engineering exam loves to test: coupling and cohesion. Cohesion, keep it high, and coupling, keep it low. Cohesion, this measures how focused a single piece of code or module is. You want a module to do exactly one job perfectly, like a dedicated login script. High cohesion makes your code reliable and easy to manage. Coupling, keep it low. This measures how interconnected different modules are. If your payment system relies too heavily on your profile picture system, changing the picture system might accidentally break payments. Low coupling keeps modules independent. Phase 4, keeping it safe and organized, which is a part of Unit 4. While your developers are writing code based on your Unit 2 design, Uh, the project manager is running background safety tasks from Unit 4. Risk management, actively predicting what could derail the project. What if the client suddenly demands massive changes? What if our database expert leaves the team? Software configuration management, SCM, tracking different versions of the code. If a developer accidentally writes code that breaks your high cohesion design, SCM allows you to roll back to the previous safe version seamlessly. Alright. The long tail, maintenance, Unit 4. Once the software is built and delivered, it enters the final phase of its life cycle, maintenance. Software is never truly finished. Software maintenance types: corrective, fixing bugs that users discover; adaptive, modifying the software to run on a new OS or environment, making sure an app works on Android 5; perfective, adding cool new features to satisfy users; preventive, cleaning up old code to prevent future bugs, which links right back to refactoring in Unit 2. Software maintenance types, I'll just repeat it: corrective, adaptive, perfective, preventive. I'll just look at my syllabus again. Software maintenance, which unit was it? Unit 4. Alright. Reverse engineering versus re-engineering. Reverse engineering. You are handed a completed piece of software with zero documentation or blueprints. You take it apart backwards to understand its architecture. Re-engineering. You take an old clunky legacy system, pull it apart, reverse engineer it, fix its design patterns, and rebuild it using modern technology. Okay, the connected big picture. Estimate the project scope and cost, COCOMO Unit 4. Write down what the client wants, SRS Unit 2. Map out the data and keep modules independent, DFT, high cohesion, low coupling. Manage code versions and track risks, SCM, risk management Unit 4. Support, update, and rebuild the software over time, maintenance, re-engineering. I'll just look at the syllabus once again. Requirements engineering, process. Did we cover refactoring? I don't think we covered refactoring. Okay, so first I'd like to start with, I'll just read it once again. I'll start from here. I'll start with change management process. handles one of the absolute certainties in software engineering. The client will change their mind. This is change management process. Okay. Whether it is a new feature request, a budget cut, or shifting deadline, change happens. If you let developers change the code whenever they want without a process, the software quickly becomes a chaotic, buggy mess. Change the management acts as a gatekeeper to ensure that every modification is evaluated, approved, and tracked systematically. The 5-step change management flows. Think of this process as a formal corporate workflow designed to keep the project stable. First would be request, then impact analysis, then approve, reject, then implement, then audit and track. First is the change request, CR, change management process. The first step would be the change request. Anyone, a client, a user, or even a developer can propose a change. They fill out a formal document called a change request. Example, we want to add a login with Google button to the landing page. Second would be impact analysis, the assessment. Before saying yes, the project manager and technical leads evaluate consequences of the request. They look at 3 primary constraints. Time. Will this delay the final release? Cost. Does this require more resources or tools? And quality or architecture. Will this break our existing design patterns, low coupling or high cohesion from Unit 2? Impact analysis, the assessment. The change request. Okay, so it starts with the request, the change request. Then we we assess the impact of the change. We assess the time, cost, and quality or architecture. Then we have the CCB review, the decision. The change request is handed over to a group called the CCB, Change Control Board. This board typically includes project manager, client representatives, and lead engineers. If the change is too expensive or risky, it is rejected. If the change adds immense value and fits the budget, it is approved. Okay, I'll repeat it once again. First, it is the request that is proposed. So first would be the change request. Second would be the assessment of the change. We assess the time, cost, and quality or architecture, how it would impact the project. And then the third one would be the final decision whether the change got rejected or approved. CCB review. Then fourth is implementation and SCM. Once approved, the developers get to work. This is where software configuration management, SCM tools like Git becomes critical. Developers create a isolated branch to write the new code. Testers run regression testing from Unit 3 to ensure the new change didn't secretly break older functional parts of the application. Software configuration management tools. Software configuration management. Where is it? Configuration management. Alright. Just the fifth part is auditing and reporting. The change is merged into the main software, documented in the release notes, and the client is notified. The project version number is updated, completing the cycle. Summary. When writing an exam answer about change management, highlight these 3 pillars. Control. It prevents scope creep. the project expanding out of control without extra budget or time. Okay. Traceability. It maintains a clear history of who changed what piece of code, when, and why. And we have got stability. It ensures the software is thoroughly tested after the change so that updates do not introduce system failures. I'll just go through it once again. Change management process. The 5-step change management workflow. Request, impact analysis, approve, reject, CCB board, implement, and audit and track. Okay, the main thing is here is the client will change their mind in change management process. Okay. Did we cover software maintenance models? I'll start with that. Software maintenance models. Software maintenance models provide a structured step-by-step blueprint for how engineering team handles changes, bug fixes, and updates after the software has been officially released to the public. Once software goes live, you can't just randomly alter the code when a bug is reported. You need a model to ensure that updates are orderly, documented, and don't accidentally crash the system. Here are the primary models used in industry to manage this phase. I'll just quickly go through the headings. First is the quick fix model, second is Osborne's maintenance model, third is iterative enhancement models, fourth is Boehm's maintenance models. Quick comparison. Okay, I'll read this one first. Maintenance model quick fix, primary focus on speed or immediate resolution, and best used for emergency hotfixes and critical patches. Osborne is for primary focuses on structured process, and it is standard corporate updates. It is best used for standard corporate updates and platform migrations. Then we have iterative enhancement, code quality refactoring, long-term projects where software must evolve gracefully. Then we have got Boehm, cost, value, and risk, enterprise level software where every change costs money. Okay, I'll read the details now. First, the quick fix model. This is the most basic, intuitive approach. It is essentially an emergency mindset. How it works: a bug is reported, the developer looks at the code, they fix the bug immediately. The code is updated. The problem: it skips updating the design documents or the SRS. Over time, the code becomes messy, unstructured, and completely different from the original blueprint. It is excellent for urgent hotfixes but terrible for long-term software health. The next one is Osborne's maintenance model. This model acknowledges that software maintenance isn't just about fixing code. It's a mini life cycle of its own, and that must handle reality shifts like new operating systems or hardware. How it works: it breaks the process into clear phases. First is identification of requirement, pinpointing what needs to change, a bug or a new feature. Analysis, assessing the impact, time, and cost. Design, altering the architectural design patterns if needed. Implementation, writing the new code. Regression testing, crucial step to ensure nothing else broke. Delivery, releasing the patch to users. I'll read it once again. First is identification of requirements, second is analysis, third is design, fourth is implementation, fifth is regression testing, and sixth is delivery. Alright, so that's the mini life cycle. Then we have iterative enhancement model. This model views maintenance as a creative loop. It treats existing system as a baseline and continuously upgrades it. How it works: instead of just patching up a leak, you actively redesign parts of the system as you maintain it. First is analyze the existing system. Second is isolate the modules that need changes. Third is design the modification using high cohesion, low coupling principles. And fourth is integrate the new features. The philosophy: this model incorporates refactoring. It ensures that every time you touch the software to maintain it, you leave the code cleaner and better structured than you found it. Okay, that's iterative enhancement model. This model views maintenance as a creative loop. It treats the existing system as a baseline and continuously upgrades it. Instead of just patching up a leak, you actively redesign parts of the system as you maintain it. So we actively redesign parts of the system while maintaining it. Okay. Then we have Boehm's maintenance model, created by Barry Boehm, the same genius behind the COCOMO estimation model in Unit 4. This model focuses heavily on economic impact and risk management. How it works: Boehm assigns a closed feedback loop based on decisions. Understanding the change: what does the user want? Evaluation: how much will it cost? What are the risks? Will this modification introduce security vulnerabilities or degrade system performance? Implementation: the code is updated only if the economic evaluation proves it is worth the risk and effort. I'll read this once again. It heavily focuses on economic impact and risk management. Assigns a closed feedback loop based on decision. Understanding the change, what the user wants. Evaluation: how much it will cost, what are the risks, will this modification introduce security vulnerabilities or degrade system performance. And implementation: the code is updated only if the economic evaluation proves it is worth the risk and effort. I'll read this once again. We were doing software maintenance model. First is the quick fix model, then Osborne's maintenance model, where we had this mini life cycle, and then we had iterative enhancement model, where we actively redesign parts of the system as you maintain it. And then we had Boehm's maintenance model. It focuses heavily on economic impact and risk management. Just read the best use for part. For quick fix, it was emergency hotfixes and critical patches. Osborne, it was standard corporate updates and platform migrations. And iterative enhancement, long-term projects where the software must evolve gracefully. And Boehm, enterprise level software where every change costs money. Okay, so after that, I would like to go with Configuration management. Uh, I'll I'll have a glass of water, then I'll come back. Alright, so configuration management. Software configuration management (SCM) is essentially the master tracking system for your entire project. To understand it, think of a massive video game development project with 50 programmers, 10 artists, and 5 writers all working at the same time. If two programmers modify the exact same file simultaneously, or if an artist deletes a folder by mistake, the project could instantly break. SCM is the set of tools, rules, and tracking processes that ensures your project never devolves into chaos. It tracks the history of every single change made to the code, documentation, or design files. The 5 core elements of SCM. When writing about SCM in an exam, it is traditionally broken down into 5 major areas: identification, version control, change control, status accounting, and audits. Then we have configuration identification. Before you can track uh, your project, you have to decide what needs tracking. You group your project items into distinct units called configuration items, CIs. Examples of CIs: the SRS document, uh, architectural design models, source code files, database schemas, and test scripts. Version control, the time machine. This is the most famous part of SCM, implemented today using modern tools like Git. It tracks the evolution of your files over time. How it works: it allows multiple developers to work on the same code base simultaneously by using branches, isolated sandboxes. When their work is done, it merges them back together. If an update introduces a terrible bug, version control allows you to hit undo and roll back to a perfectly stable older version of the software. Change control. This links directly back to the change management process we discussed earlier. It ensures that changes to a logged, finalized version of a document or code base known as baseline are not done recklessly. Any major change must be analyzed for risk, cost, and impact, and then formally approved by the Change Control Board (CCB). Configuration status accounting. This is the reporting and record keeping side of SCM. It answers administrative questions like what changes were made to the software last week, which version of the code is currently deployed for the customer, how many change requests are currently pending approval. Then we have configuration audits. Before software is shipped to a client, an audit is performed to verify that the system matches the requirements. Functional audit. Does the software actually do everything the SRS said it should do? Physical audit. Are all the files, code, user manuals, and installation scripts properly organized, updated, and ready for delivery. What is a baseline? Crucial exam concept. A baseline is an official milestone in the software development cycle. When a phase is completed, for instance, when your team finishes writing the SRS document in Unit 2, the document is reviewed, approved, and formally baselined. Once an item is baselined, it is logged. A developer cannot just open the file and change its indents. To alter it, they must formally go through the change control process. This prevents project's foundation from shifting constantly while people are trying to build on top of it. Think of SCM as the safety net for software delivery. It keeps a historical timeline of the project version control. It protects finalized project milestones from unauthorized modification baselines. It ensures total transparency regarding who changed what, when, and why. Status accounting and audits. Now that we have covered change management, maintenance model, and configuration management, okay, I'd still like to check whether I've completed, run through everything in Unit 4. Okay, I'd like to start with risk management. Okay, in software engineering, a risk is a potential problem that might happen in the future. If it is actually happens, it turns into an active issue that can cause delays, budget overruns, or complete project failure. Risk management is the proactive practice of spotting these hidden icebergs early and deciding how to steer the ship around them before you hit them. The 3 types of software risk. Before looking at the process, it helps to understand what kind of risk project managers track. Project risks, threats to the schedule or resources. Example, our lead developer might quit in the middle of project, or the necessary hardware components might be delayed in shipping. Project risks, technical risks, and business risks. Technical risks, threats to quality, design, and performance of the software. Example, the new open source library we plan to use might turn out to be buggy or incompatible with our Unit 2 architectural design. Business risks, threats to the commercial viability of the software. Example, a direct competitor might launch an identical product before we finish ours, or the client might run out of funding entirely. The risk management life cycle, the 4 steps. A project manager continuously runs a 4-step cycle to keep risks under control throughout the software development life cycle, SDLC. The first one is identification, then risk analysis, planning and mitigation, monitoring. Risk identification. The team sits down at the beginning of the project and during milestones to brainstorm every possible thing that could go wrong. They create a master list called a risk register. Techniques, looking at historical checklists from past projects, interviewing team members, and examining strict deadlines. Second is risk analysis and assessment. Not all risks are created equal. You can't spend time and money fighting every single potential issue. So you evaluate them based on 2 factors. Probability, how likely is this risk to happen, scale of 1 to 5, and impact, how badly it will hurt the project if it does happen, scale of 1 to 5. You calculate the risk exposure or risk priority using a simple formula. Risk exposure equals probability into impact. High probability, high impact risks are flagged as critical priorities. Risk planning and mitigation (RMM). Uh, RMM stands for Risk Mitigation Monitoring and Management. For every high priority risk, you must design a strategy. Avoidance mitigation, taking active steps right now to reduce the likelihood of the risk happening. To mitigate the risk of a developer quitting, you ensure thorough documentation and cross-train another team member on their tasks. Then, contingency planning, management, your plan B. What will you do if the mitigation fails and risk becomes a reality? If the developer leaves, the contingency plan outlines a pre-vetted freelance agency you can hire immediately to step in. Risk monitoring. Risks are dynamic. Their likelihood changes over time. A risk that was highly probable in week 2 might disappear entirely by week 10 once that phase of code is finished. The project manager constantly checks the risk register during weekly status updates to see if new risks have emerged or if old ones can be archived. When writing about risk management, highlight the core goal, shifting a project from being reactive, putting out the fires as they happen, to proactive, preventing fires from starting. RMM framework as your structural outline for addressing critical threats. I'll just read once again. Risk management I was doing. 3 types of software risk: the risk management lifecycle identification, analysis and assessment, planning and mitigation, monitoring. Then we had risk planning and mitigation, RMM, risk mitigation, monitoring and management. First we had mitigation, then we had management. Then we had risk monitoring. Okay. Now I would like to start with project planning. If software engineering is like going on a massive road trip, coding is the driving part, but project planning is sitting down with the map checking, the fuel cost, calculating how long it will take, and deciding who is driving which shift. The ultimate goal of project planning is to eliminate guesswork so that the team can deliver the software on time and within budget. The core elements of project planning. Project manager must answer 4 major questions during the planning phase. Scope. What are we building? Estimation. How much effort will it take? Scheduling. When will it be done? And resource allocation. Who is doing it? Here is how a project plan is built step by step. Defining the software scope. Before you can estimate anything, you must establish the boundaries of the project. Scope defines exactly what features will be included and, just as importantly, what will not be included to prevent scope creep. Example, the app will support user login and credit card payments, but it will not support crypto payments in this version. Software estimation: size, cost and effort. Once you know the scope, you figure out how big the project is. Your syllabus highlights 2 major ways to calculate this: decomposition techniques, breaking the project down into smaller functional pieces like login, module, database setup, UI design, and estimating each piece individually, and empirical estimation models, COCOMO and FPA, using historical data and mathematical formulas. Kokomo takes your estimated lines of code and calculate how many months of effort and money the project will require. Then we had functional point analysis, calculates size based on the number of inputs, outputs, and external files. Then we have project scheduling, the timeline. Now that you know how much work needs to be done, you map it out across a calendar timeline. Project managers use two classic visual tools to schedule tasks. Uh, Gantt charts, a horizontal bar chart that lists all the tasks on the left, and a calendar timeline across the top. It visually shows exactly when each task starts, how long it takes, and who is assigned to it. PERT CPM networks, a flow diagram consisting of boxes, tasks, and arrows that maps out dependencies between tasks. You cannot start testing until coding is finished. It helps identify the critical path, the absolute longest sequence of dependent tasks that determines the shortest possible time to finish the project. If a task on critical path is delayed by 1 day, the entire project is delayed by 1 day. Resource allocation. This is organizing your assets. It involves mapping out your people, how many front-end developers, back-end developers, and testers are needed. Hardware software tools, cloud servers, laptops, testing licenses, and space, office space, or remote collaboration setups. The output, the software project plan, SPP. All of this planning work is compiled into a single master document called the Software Project Plan, SPP. This document serves as the absolute source of truth for the entire team. Throughout the rest of the SDLC, the project manager will constantly look back at SPP to track progress. If the actual progress begins to drift away from the plan, the manager steps in with tracking and control measures to bring the project back on course. Okay, the core points are objectives, defining scope, minimizing uncertainty, and establishing a baseline for tracking. Second is estimation tools, mentioning Kokomo and FPA for effort or cost calculation. Then we have scheduling tools, describing Gantt charts for timelines, and PERTs or CPM for finding the critical path and task dependencies. Back to my syllabus. Okay, wait. I'll just read this again. Core elements of project planning: scope, estimation, scheduling, resource allocation, defining the software scope. Alright. I'll go to unit I'll go to unit 3, security testing. I'll have a glass of water. I'll take a break, a quick break. Alright. Security testing is a highly specialized type of software testing. While standard testing checks if the software works correctly, security testing checks if the software can defend itself from an attack. Its primary goal is to find hidden vulnerabilities, flaws, or backdoors in the system that a malicious hacker could exploit to steal data, crash the website, or steal money. The six core attributes of security testing. When engineers test the security of a web application or system, they measure it against six fundamental pillars, often referred to as the CIA triad plus authorization, authentication, and non repudiation. Confidentiality, ensuring that sensitive information is only visible to the people who are authorized to see it. Testing check. Can a standard user access another user's private profile details by manipulating the URL? Is sensitive data encrypted? Integrity, ensuring that data cannot be altered or tampered by unauthorized users while it travels across the internet or sits in a database. Testing check. Can a user intercept a network request and change the price of an item from $100 to $1 before submitting their order? Authentication, verifying the digital identity of the person logging in. It answers the question, are you truly who you say you are? Testing check, is the password hashing strong? Can a hacker bypass the login page using basic brute force password guessing tools? Authorization, checking the permission of an authenticated user. It answers the question, now that I know who you are, what are you allowed to do? Testing check, can a regular student log into university web portal and accidentally gain access to the administrator dashboard where grades are changed? Fifth is availability, ensuring that the application stays up and running for legitimate user even during an unexpected traffic spike or malicious attack. Testing check, how does the system handle DOS/DDoS, denial of service attack, where a hacker floods the server with millions of fake requests simultaneously? Non-repudiation, ensuring that a user cannot deny performing a specific action or transaction on the system. Testing check, does the system keep secure, unfalsifiable log files tracking critical actions like tracking exactly which administrator authorized a massive financial transfer? Common security testing techniques. Security testers use a variety of active testing methods to find flaws. Vulnerability scanning, using automated software tools to scan an entire system looking for known security holes, outdated software libraries, or weak configuration. Penetration testing, ethical hacking, a hands-on approach where a security expert actively pretends to be a malicious hacker. They try everything they can to bypass firewalls, crack passwords, and break into the database to find real-world weak points. Security auditing, a systematic formal review of the source code and configuration files line by line to verify compliance with security regulations and best practices. When writing about security testing, remember what it is specialized form, that it is specialized form of quality management. Instead of testing for functionality, what the system should do, it tests for vulnerability, what the system should never allow a user to do. We have now broken down almost every core element of testing from Unit 3. Okay, Unit 3, Software Testing Fundamentals. I think we covered software testing fundamentals. I don't remember. Okay, here. We covered terminology, core principle of software testing, and the two fundamental approaches V&V, verification and validation. The core principles were testing shows the presence of defect, not their absence. Exhausting testing is impossible. Early testing and defect clustering. Alright. Now from Unit 2, my weak point. I think I'll do Unit 2 as a whole. I'll jump to Unit 1. No, software process framework. I did this but I forgot. I'll have to check this again. Software process framework. Communication planning, modeling, construction, deployment. What was it exactly? Umbrella activities. Core activities and umbrella activities. Umbrella activities were software project tracking and control, risk management, software control, software quality assurance, SQL, formal technical reviews, FDR, software configuration management, SCM. Alright. I'll just do Unit 2 as a whole. Okay, so part 1 is requirements, engineering and SRS. Before writing any code, you need a contract that specifies exactly what the system should do. This process is called requirements engineering. Requirements analysis. You interview the client, look at their current workflow, and sort their needs into two buckets: functional requirements, what the system must do, and non-functional requirements, how well the system must perform. SRS, software requirement specification. This is the official master document that acts as a bridge between the client and the developers. It contains all gathered requirements. Once approved, it is baselined. Then we have part 2, requirements modeling tools. To make SRS easy for developers to visualize, we use diagrams to model how data and users interact with the system. Data flow diagrams, DFD. A DFD maps out how data moves through your system. It uses specific shapes to show where data comes from, how it changes, and where it gets stored. Level 0 DFD, context diagram. A high-level overview showing the entire system as a single bubble, focused only on external inputs and outputs. Level 1 DFD explodes that single bubble into major sub-processes, separating process order into verify payment, check inventory, and generate receipt. Use case modeling. A use case diagram shows the system from the user's perspective. It answers two questions: who is using the app, actors, and what goals they are trying to achieve. Use cases. Example: a stick figure representing a customer connected by two lines to bubbles labeled view product, add to cart, and checkout. Part 3, software design and architecture. Once you know what the data is doing, you design the code's internal structure. A great design ensures that when your application grows, it doesn't turn into tangled mess of spaghetti code. Cohesion versus coupling, the ultimate exam topic. Your design should always aim for high cohesion and low coupling. Cohesion, keep it high. This measures how focused a single module or function is. A highly cohesive module does one thing and one thing only. A payment processor class only handles credit card transactions. Coupling, keep it low. This measures how dependent different modules are on each other. If module A breaks every time you make a tiny change to module B, they are highly coupled. You want them to be loosely coupled so you can edit or swap out one part of the app without crashing the rest. Design patterns and architectural styles. Instead of reinventing the wheel, software engineers use proven templates to solve common architectural problems. Design patterns. Reusable solutions to local coding problems. Singleton pattern ensures a class only ever creates one single instance of itself throughout the app's life cycle. Then we have architectural styles, the high-level blueprint for the entire application. Examples include client-server architecture. Your app requests data and a central server provides it. Layered, entire architecture, separating code into distinct structural layers. Example, presentation layer, business logic layer, database layer. Refactoring. Refactoring is the process of cleaning up, restructuring existing code without changing its external behavior. You do this to improve internal cohesion, reduce coupling, and make the code easier to maintain, effectively clearing out technical debt. If you get okay, elicit model design. Elicit, gather requirements from the user and document them in the SRS. Model, visualize the data, systems data and user steps using DFTs and use cases. 3. Design, structure the code using architectural styles, keeping cohesion high and coupling low to ensure the system remains easy to refactor and maintain over time. Okay. So in Unit 2 we cover many things: DFT, use case modeling, software, SRS, coupling, cohesion, design pattern, refactoring. I am still not confident with Unit 2. Actually, I'm not confident with the entire syllabus, but Unit 2 is hitting hard. I think I will let's see if this works for me. I'm confused. What is refactoring? Technical debt and codesmith, signs that code is poorly structured and likely to break down the line. We refactor to improve software design. It sharpens the architecture, steering it back towards high cohesion and low coupling ideals. Make code easier to understand. It makes the code readable for other developers on your team. Help find bugs faster Clean code makes hidden logical errors stand out immediately. Speed up future programming. It is much easier to add new features to clean modular code bases than to a tangled mess of spaghetti code. Common code smells that requires refactoring. How do you know code needs to be refactored? These are the classic warning signs. Long methods functions. A single function that is 200 lines long and tries to do 5 different jobs. Low cohesion. Duplicate code. The exact same block of code copy pasted in 3 different places. If you find a bug in that logic, you have to fix it in 3 separate times. A large class. A class that has too many variables and responsibilities. Dead code. Variables, functions, or entire modules that are completely unused but still sitting in the code base, causing confusion. How refactoring actually works. Techniques. Refactoring is done in tiny systematic steps. After every minor change, you run your automated tests just like JUnit from Unit 3 to ensure you didn't accidentally break anything. Here are few standard techniques. Extract method. Breaking things down. If you have a massive complicated function, you pull a chunk of code out of it and turn it into its own independent well-named small function. Before, a single function handles calculating prices, applying taxes, formatting currency, and printing a receipt. After, the main function calls 4 separate cohesive functions: calculate price, apply tax, format currency, and print receipt. Okay. Extract method is breaking things down. Rename variable method. Changing ambiguous, confusing names to clear descriptive ones. Before, int d equals to 86400, int seconds in a day, 86400. Inline method. The opposite of extracting. If a function is so small and simple that its body is obvious as its name, you get rid of the function entirely and just paste the code directly where it's needed to eliminate unnecessary clutter. Refactoring versus rewriting. It's common to confuse these two terms, but are fundamentally different approaches. Feature code base. You keep the existing code and clean it up incrementally. You throw away the old code entirely and start from scratch. Alright, that's the difference. That's the first difference. Code base. Risk factor. Low risk, done in small steps, backed by constant testing. High risk, takes a long time and can introduce brand new bugs. External behavior remains exactly the same. The user notices zero functional changes. Rewriting may change, improve, or include completely new features. Alright, that was external behavior summary. It alters the internal structure of code while leaving its external behavior unchanged. Its primary goal is to fight technical debt, to eliminate code smells. It directly supports long-term software maintenance by keeping the code base clean, modular, and easy to scale. I am still confused. I am still not well versed with the syllabus. Okay, this is what I'll do. Can't see anything. I don't know what's happening. Just try this once again. Never mind. I'll think of something else. What should I do? How do I got the basic idea. I have a blueprint in my mind, but I still won't be able to write answers. I think I should move on to question answers. Okay. Okay, how many questions are there? 19. Define software engineering, discusses its importance in modern system development. Software engineering is defined as the systematic, disciplined, quantifiable approach to the development, operation, and maintenance of. I think this is the IEEE definition, standard definition. That is the application of engineering principles to software. It is crucial because modern software is incredibly complex. Without structured principles, software projects suffer from low quality, missing deadlines, unmanageable code bases, and massive budget overruns. It ensures predictability, scalability, security, and maintainability. What is meant by the term software crisis? State some of its major symptoms. The software crisis refers to a set of chronic problems encountered during the development of computer software, particularly in the late 1960s and onwards, where software could not be delivered efficiently. Key symptoms include project exceeding original cost estimates significantly, schedules slipping past target delivery milestones, final software being highly inefficient or full of defects, software failing to meet the actual requirements of the customer, difficult, expensive, or impossible long-term maintenance. Detail two common software engineering myths and explain the underlying reality. Myth 1, if we fall behind schedule, we can add more programmers and catch up. Reality, Brooks Law. Adding people to the late software project makes it even later. New members require training and ramp-up time, which diverts existing developers and inflates communication overhead. Myth 2. A general statement of objectives is sufficient to begin writing programs. We can fill in details later. Reality. Unambiguous or incomplete initial objectives lead to disastrous miscommunication, structural flaws, and massive rework expenses later in the SDLC. Question 4. Compare and contrast the waterfall model and the agile model. The waterfall model is a linear sequential framework where development flows strictly downwards through distinct phases: requirements, design, implementation, testing, maintenance. Change is difficult to implement once a stage is locked. Conversely, the agile model is iterative and incremental. It breaks development into short 2-3 week sprints, welcoming change requirements even late in development, emphasizing continuous stakeholder feedback and working software. Explain the conditions under which the spiral model is highly recommended. The spiral model is a risk-driven process model that combines iterative prototyping with the controlled systematic aspects of the linear model. It is highly recommended for large-scale, expensive or business-critical projects where failure is not an option, projects with high degree of uncertainty or complex technical risk, systems requiring frequent custom evaluation and continuous risk mitigation steps at every layer. Unit 2. Modeling. What is a software requirement specification SRS document and why is it considered a baseline? An SRS document is the formal statement of a system's functional and non-functional requirements. It outlines exactly what the software must accomplish without stating how it will be technically implemented. It acts as a baseline because once signed off by both the client and development team, it is locked under configuration control. Any future change requests are verified against this baseline to monitor scope creep and handle modification systematically. Question 7. Explain the structural difference between a level 0 data flow diagram and a level 1 DFT. A level 0 DFT, known as the context diagram, models entire system as a single central process bubble interacting with external entities, sources and sinks of data. It provides zero internal details. A level 1 DFT decomposes that single process bubble into its major subprocesses, tracking how data flows internally between subfunctions, data warehouses, data stores, and external entities. Question 8. Differentiate between coupling and cohesion. What is the golden rule of software design? Cohesion measures the functional strength or focus of a single module. High cohesion means a module does one dedicated job perfectly. Coupling measures the degree of interdependence between separate modules. High coupling means changes in one module unexpectedly break functionality in another. The golden rule of software design is to achieve high cohesion and low coupling to maximize maintainability and scalability. Question 9. What is refactoring? Cite its key objective. Refactoring is the process of altering the internal structure of software code to optimize its design, readability, and modularity without changing its external operational behavior. Its key objective is to eliminate technical debt and eradicate code smells like duplicate code or bloated routines while keeping all functional features fully intact. Question 10. Explain layered architectural style with its real-world application. A layered entire architectural style organizes a software system hierarchically into separate structural layers, where each layer provides services to the layer immediately above it and consumes services from the layers immediately below it. A classic example is a web application separated into three tiers: a presentation layer, UI, a business layer, co-processing, and a data access layer, database management. Question 3. Quality management. Differentiate between white box, black box, and gray box testing. Testing type: white box. Testing type: knowledge of internal code, primary focus. White box: full access to internal source code, structure and logic paths, primary focus. Verifying internal loops, conditional branches, statements, and paths. Black box: no knowledge of internal code or data implementation structure, primary focus. Validating external software behavior against formal specifications, inputs. Gray box, partial access knowledge of internal data, layouts, and logic. Primary focus, designing functional test cases informed by underlying architectural constraints. Question 12. Trace the distinct operational levels of testing in order: unit, integration, system, and regression. Unit testing tests the smallest isolated atomic blocks of code, such as individual functions or methods. Integration testing verifies that multiple interacting modules connect, communicate, and transfer data correctly when joined. System testing validates the completely integrated software package as a unified whole against the original specification. Regression testing reruns existing test cases after code changes are made to guarantee that new additions did not inadvertently break older features. Question 13. How do Selenium and JUnit assist automated testing workloads? JUnit is a code-level unit testing framework tailored for Java. It allows developers to write automated assertion scripts to test functions instantly during compilation. Selenium is an open-source browser automation framework. It allows testers to write scripts that automatically simulate human UI interactions within web browsers, clicking elements, logging input, scrapping output to run functional tests at a scale. Question 14. Outline the key objectives of security testing. Security testing identifies systematic vulnerabilities, configuration flaws, or digital backdoors within an application. It verifies that the system successfully enforces 6 fundamental security parameters: confidentiality, integrity, authentication, authorization, availability, and non-repudiation, ensuring full resilience against external cyber attacks. Unit 4. Managing software projects. Question 15. Explain the COCOMO model for estimation. State its base effort equation. The constructive cost model COCOMO is an empirical mathematical estimation model that predicts a software project's effort duration and ideal sizing based primarily on the size of the software measured in thousands of delivered lines of code. KLOC. The fundamental base equation for effort estimation takes the following structure: effort equals A into KLOC to the power B, where A and B are specific empirical constants determined by the classification mode of the software: organic, semi-detached, or embedded. What does the acronym RMMM mean in risk management? Explain its components. RMMM stands for Risk Mitigation, Monitoring, and Management. Mitigation: proactive operational steps executed to minimize the overall probability that a potential risk will occur. Monitoring: continuous surveillance of key project metrics to evaluate whether specific risks are becoming more or less likely over time. Management: executing a pre-planned Plan B contingency steps if the mitigation efforts fail and risk materializes into an active issue. Question 17. Explain the 4 distinct categories of software maintenance. Once software goes live, maintenance activities fall into one of the 4 distinct functional classes. 1. Corrective maintenance. Diagnosing and fixing active bugs or faults reported by users in production environments. 2. Adaptive maintenance. Altering software to ensure compatibility with shifting external environments. Example, a new OS patch or hardware upgrade. 3. Perfective maintenance. Integrating cool new optical features or layout enhancements to satisfy ongoing user requests. 4th is preventive maintenance. modifying code structures to optimize readability, clean legacy code, and prevent future bugs before they manifest. Question 18. Differentiate between reverse engineering and re-engineering. Reverse engineering is a purely analytical process where an existing finished application is broken down backward to understand its internal design, architecture, or original source requirements without changing it. Re-engineering is a broader active restructuring life cycle. It encompasses reverse engineering first to understand a legacy system, then cleaning, altering, and modernizing the system architecture to rebuild it completely into a high performance modern product. Question 19. Describe the change management process within software configuration management. The change management process coordinates how modifications to software assets are handled. It follows a structured flow. A formal change request (CR) is submitted. Technical leads complete an impact analysis evaluating time, cost, and design effects. A change control board (CCB) formally reviews the request to approve or reject it. If approved, developers build it in an isolated branch, regression tests to ensure stability. Finally, the asset baseline is updated with a revised version number. I will have a glass of water and I'll come back in a short while. Okay. Still, I think there's a lag in my understanding, lack of understanding. How should I proceed? I'll just take a look at the syllabus once again. I think I will open. I think I'll go with. I'll read this. I have this book. What steps should I take? Like, how should I proceed with the syllabus? I don't even know. Okay, I'll just. What should I do? I think practice will help. What is the core difference between waterfall model and agile model regarding how they handle changes in project? Uh, waterfall model. Waterfall model, how they handle changes in a project, follows a rigid blueprint, rigid, not a blueprint, rigid sequence of steps, while agile model focuses on what does it focus on? While agile model focuses on, I don't know how to continue. Quick rapid development and changes continuously. Okay, waterfall is predictive, agile is adaptive. In software design, what is the golden rule regarding cohesion and coupling? Okay, cohesion should be high and coupling should be low. Because it stated that cohesion is like do one thing exceptionally well, and coupling was one module should not depend on another, so coupling should be low. What is the difference between black box testing and white box testing regarding the tester's access to the code? In black box testing, knowledge of the internal code is not required. In white box testing, knowledge of the internal code is required. Okay, after studying, at least I know this much. Software maintenance are you performing? Oh, I don't remember this one. Software maintenance. what were the types of software maintenance? There was perfective, and there was adaptive, I guess. Although I'm not sure, I'll still make a guess. Okay. What is the name of the formal group board? It was CCB. Change control board. Change control board. Yes. I think such practice questions will help me with remembering the concepts. Active recall. What is the software crisis that happened? In simple terms, what is software engineering? Okay, so firstly, what was going wrong during software crisis? Okay. Projects kept exceeding deadlines and budget. Filled with bugs and often fail to deliver what the client actually wanted. Okay, what is the difference between a level 0 diagram, level 0 DFT is a simple diagram level 1 DFT has more detail. It was level 0 DFT is also called a context diagram. I couldn't remember this point. As a single process bubble, it only shows how data enters and leaves the system form. external entities given zero internal details. Level 1 DFT explodes that single bubble to reveal the major internal subprocesses, data stores, and how information moves between them. Okay, the third question is, imagine you write a new feature for your app and it works perfectly. However, your project manager insists that you run your entire test suite again to make sure this new feature, this is regression testing. Okay, this helped me build confidence with the short answers, but I don't think I'd be able to write long answers. Anyways, let me practice the short answers first. In Barry Boehm's COCOMO model, what is the primary metric or input used to calculate how much effort and time a software project will take? I don't remember this one. How much effort and time a software project will take? I think it was probability. I am wrong, I guess. Probability and what was the other thing? I don't. Input. I am wrong, I guess. I don't remember it very well. Or it may be KLOC, A into KLOC power B. It could be that also. There were impact. Okay, it was impact. Risk management. The primary input or metric is the K-log, thousands of lines of code. This model takes this physical. Okay. What's the difference between reverse engineering and re-engineering? In reverse engineering, we look at the code and try to understand it going backwards. It does not make sense. I'm not able to make sense out of what I'm thinking. Like, we have this code and we are understanding, we have this project. We look at the going backwards. Okay, I'll just keep it like that. And re-engineering is when we take a piece of code and make changes in it using modern software tools. Okay, I'll just read it out. Reverse engineering is a purely analytical process where you look at existing code look at an existing product and break it down backward to understand how it works or reconstruct its original design blueprints. You don't change anything. Reengineering is the full life cycle where you take that old system, reverse engineer it to understand it, and then effectively modify and rebuild it using modern technology to make it better, faster, and cleaner. Round 2 score is 4 out of 5. Okay, CKLOC. I need to remember that. In the prototype model, you build a quick rough version of the what is the main okay, I don't know this one. What is the main danger or myth? Okay, the customer thinks that it is the final working model. They do not think of the prototype as something to be thrown away. When a customer sees a slick working user interface, they often think, wow, this looks almost finished. They don't realize that underneath the surface there is no real database, no security, and the code is held together by duct tape. They get impatient when you tell them it will take another 6 months to build the actual production ready system. Alright. Design patterns. Can you name or describe just one common reason why developers use the standard design patterns instead of writing custom code structures from scratch every time? Because it's, I don't know, writing from scratch every time. One common reason, because it may be time consuming. I don't know, I'm just guessing. I think I did this one incorrectly, but anyways, let's. Okay, wow. Exactly, time consumption and efficiency are huge parts of it. By using design patterns, developers don't have to spend hours or days reinventing the wheel to solve common architectural problems. Design patterns act as proven battle-tested blueprints that are already known to work. This not only saves immense time during development but also makes the code base instantly understandable to any new programmer who joins the team and recognizes the pattern. The third question is, what is the difference between verification and validation? Okay, I have to take help of the hint. Verification and validation. Verification takes place before the execution of program. Validation takes place after the execution of program. verification includes static checks like code reviews, walkthroughs, and inspection. Things you do before running the program to ensure the code conforms to the specifications. Are we building the product right? Validation involves the actual dynamic execution of the program with real test cases to check if it matches what the user actually wants. Are we building the right product? Okay, so the fourth question is, when mapping out a project timeline using PERT CPM chart, what is the critical path? Why is a project manager so obsessed while tracking it? Critical path. I don't remember anything about this one. I don't remember. The critical path is the absolute longest sequence of dependent tasks from the start of a project to the very end. Project managers are obsessed with it for one crucial reason. It tells you the shortest possible time required to complete the project. If any task on the critical path is delayed by even one single day, the entire project completion date slips by a day. Tasks not on the critical path have something called float or slack, meaning they can be delayed a little bit without impacting the final deadline. I'll read this once again. Basically, okay. In software, in SCM, what does it mean when document or baseline? I don't know this. Baseline. Oh, wait, I could have written something about it. When a document like your SRS or a piece of code is baseline, it means it has been formally reviewed, agreed upon, and logged under version control. Here is how it works in simple terms. Before it's baseline, developers can edit, rewrite, and change the file freely whenever they want. After it is baseline, it becomes the official source of truth. Nobody is allowed to touch or change it directly anymore. If someone wants to make a modification, they must submit a formal request CR to the Change Control Board CCB to get approval first. It prevents a project from descending into total chaos where people are randomly modifying files. I guess I'll go with more questions. When I hit walls like these where I am not able to answer a question, I get to learn, so I think I should practice more questions. Okay, 3 questions at a time. What is the main purpose? Who needs to sign off? Answer to the first question. SRS contains all the details regarding the project, and who needs to sign off, I don't know, so I'll just skip that part. When we talk about refactoring code, what are we actually changing and What must remain completely the same? We are changing. What we are changing? We are changing the internal. We are changing the internal code without actually changing how it works externally. The third part is, can you list the 4 main operations? Okay. So the first one was unit testing. The second one was integration testing. Was it integration testing? Unit testing, yes, it was integration testing. The third one was, don't remember the third one. Unit testing, integration testing. The fourth one was, what was it? Regression testing. Okay, this is what I know. This is what I remember. I'll just read out what both the key people who sign off on it are both the client and the development team, making it a formal contract before coding kicks off. Both the client and the development team. That's what I was missing. Second is second I did it. System testing. Okay, I forgot. Wait. It is acceptance testing. Unit testing, integration testing, system testing, and acceptance testing. Alright. What is the name of the specialized testing framework used specifically to automate UI interactions in web browsers, like automatically clicking buttons or typing text into a web form? For the fourth question, what is the name of UI interactions? Selenium. And as for the fifth one, in risk management, one was mitigation, management, I don't remember, I'm just writing. Mitigation is correct, I know. Management, and I'll just submit this. This is what I know. Monitoring. I forgot monitoring. Tracking the project matrix to see if the risk is becoming more likely. Mitigation is proactive steps to prevent the risk from happening. Monitoring is tracking the project matrix to see if the risk is becoming more likely. And management is your contingency plan B to handle the situation if the risk actually turns into a real problem. Alright. Few more. Actually, more, not a few more. I need to practice a lot. In software architecture, what is the key difference between... Okay, I don't know this one. I'll just keep this blank. Cyclomatic complexity. Okay, I don't know any of it. I'm glad I continued with the practice. I don't know any of the answers. Monolithic versus microservices architecture. Think of how you structure your entire software code base. Monolithic architecture. The entire application is built as one single massive unit. The front end, back end, and the database logic are all tied together in a single repository. The problem: if you want to change one tiny feature, you have to redeploy the whole massive app. If one small part crashes, the entire system goes down. Microservices architecture. The application is broken down into a collection of small independent services that talk to each other over the network. Example: a separate service just for user authentication, a separate one for payment processing. The benefit: if the payment service crashes, users can still browse product. You can scale or update individual parts of the app without touching the rest. Cyclomatic complexity. In simple terms, cyclomatic complexity measures the number of linear independent paths through a program's source code. Essentially, it counts how complex your conditional logic is by looking at decision points like if, else, while, and switch statements. Why testers care? It tells a QA engineer exactly how many test cases they need to write. If a function has a cyclomatic complexity of 5, it means that there are exactly 5 distinct logical pathways through that code. So you need at least 5 unit test cases to achieve 100% path coverage. Function point FP analysis versus line of code LOC. When estimating how big a project will be before you build it, lines of code LOC. This depends entirely on the programming language. Implementing a feature might take 100 lines of code in C, but only 10 lines of code in Python. You can't accurately count lines of code before the code is actually written. Function point FP analysis. This measures size based on the functionality requested by the user, completely independent of the programming language. It counts things like how many inputs, forms, how many outputs, reports, and how many external interfaces will the app have. Why PMs prefer FP? You can calculate function points right during requirements phase, Unit 2, just by looking at the SRS, long before anyone writes a single line of code. Let's pivot back to something more familiar. Okay. We are analyzing a system to check if it analyzing a system's source code line by line. I think it is not integration test. It should be either walkthrough or an inspection. I'll just go with walkthrough. Alright, it's inspection. Walkthrough. This is informal. The developer who wrote the code leads a meeting and walks the team through the logic to explain how it works. The goal is just to understand the code and find obvious bugs. Inspection. This is highly formal, strict process. A trained team reviews the code line by line using a specific checklist to look for defects, security vulnerabilities, or violation of corporate coding guidelines. It involves official rules like moderator and a reader, and the results are formally documented. Okay. Imagine your university professors give you a teammate's project code and a 10-point checklist telling you to verify that every variable name follows the exact naming standard required by the department. Okay, this one would be a walkthrough. Is it? Walkthrough, informal casual guide. Inspection is formal, checklist driven audit. Cohesion versus coupling when designing. Software reliability versus software quality. Listing definitions in Unit 3. Software quality, this is the umbrella term, refers to how well the software conforms to both functional requirements, what it does, and non-functional requirements. Performance, security, maintainability, usability. Software reliability, this is a subset of quality. It is the probability that the software will run completely failure free for a specified period of time in a specified environment. It is measured using metric like MTBF, mean time between failure. Let's test your intuition on these new terms with two fresh questions. Alright. User password, sending emails and uploading profile pictures all at once. Coupling. If a system crashes once every I'll have to read this once again for question 2. If the software system crashes exactly once, which software quality I think it is software reliability. When a single class it has low cohesion, it is scattered. Okay. Third question. The spiral model, what is the first thing you must do? It was about like talking with the customers, right? Customers, talking to customers. And question 4, sorry. In black box testing, I don't remember what was it. I'll just leave the fourth question. Boundary value analysis, BVA. Objective identification and risk analysis, the core of the spiral model. But the objective identification and risk analysis, the spiral model is entirely risk driven. At the start of every loop quadrant, you don't just jump into coding, you first identify what needs to be achieved in this phase. Look at the potential risk involved and find ways to mitigate them. If a risk is too high, you might even pivot before building anything. Boundary value analysis, BVA. When you specifically test the exact boundaries of an input range like 17, 18, 19 for lower edge and 59, 60, 61 for the upper edge, it is called boundary value analysis, BVA. Quick rule of thumb: if you test a number right inside the range, that's equivalent partitioning. If you test exact edges, min minus 1, min plus 1, that's boundary value analysis. Okay, question 5. You test a system by giving it an absolute massive overload of data. What type of non-functional testing are you doing? I don't remember. I read about it, I know, but I don't remember. Question 6. Which software development life cycle linear sequential model? I think it's the spiral one. Or maybe not. I think, wait, I'll just go with waterfall model. Even though I'm not 100% sure, I'll just go with waterfall model. I don't remember the fifth one, so I'll just leave it blank. Stress testing. When you push a system way past its limit to intentionally break it, you are performing stress testing. I forgot this one. Anyways, load testing checks how the system handles the expected peak traffic. Stress testing: what happens when you completely overload it? Throwing 10,000 users at a site built for 1,000 to find the breaking point and see if it crashes gracefully or catastrophically. Difference between I don't know. I don't know either of. Functional versus non-functional requirements. Functional requirements. These define what the system must do. They are explicit features, functions, and tasks the system must execute. Examples: the system must allow users to log in using their email. The app must calculate the total amount, including a 10% tax. Or the system must send an automated email confirmation upon registration. Non-functional requirements. These define how the system should perform while doing those tasks. They specify the quality attributes, constraints, and characteristics of the system: performance, security, usability, reliability. Example: the login page must load within 2 seconds. All user passwords must be encrypted using AES-256, or the system must be accessible to 99.9% of users at any given time. I'll just read the text in bold once again. Functional requirements: what the system must do, and non-functional requirements: How the system should perform. Uh, okay. Analogy. If you are buying a car, the functional requirement is that it must take you from point A to point B and have four wheels. The non-functional requirement is that it should sleek, go from 0 to 100 km per hour in 4 seconds and have a 5-star safety rating. Alright. Second one. Gantt chart versus PERT chart. I don't know if I'm pronouncing it right. Both are essential project scheduling tools used in Unit 4, but they visualize the project timeline differently. Gantt chart. This is a bar chart that shows project schedule over a timeline. Visuals. Tasks are listed vertically on the left and time intervals, days/weeks, are listed horizontally across the top or bottom. Each task is represented by a horizontal bar. The length of the bar shows how long the task will take. It is excellent for seeing when tasks start, end, and overlap. PERT chart, program evaluation and review technique. This is a network diagram, a flowchart made of nodes, circles or boxes, and arrows. Visuals. It doesn't look like a calendar. Instead, it looks like a web of interconnected tasks. Arrows show the sequence and dependencies. Example, task B cannot start until task A is completely finished. It is used primarily to calculate the critical path and map out complex task dependencies. It is functional. Non-functional. Okay, if a requirement states the system must display an error message in red if a user enters an incorrect password. This is non-functional. Okay, I'm getting this. The core of the requirement is describing a specific feature and behavior of the application. The system must check the password and display an error message. Because it defines an active behavior in specific step the software mistake, it falls squarely under functional requirements. The fact that text appears to be read is just a user interface detail. Alright. Final question. Which is functional or non-functional? Non-functional. Finally. I'll have a glass of water and I'll come back in a second. Okay, I'll just start a new chat. was a typo. I just give short questions related to this syllabus. Oh my god. I can't. How do I answer so many questions at a time? Unit 1. What is the software crisis and what are its main causes? This is 1960s, I guess. I don't know whether it was 1950s and 60s or 1960s and 70s, but anyways I'll go with 1960s and 70s because developers deliver software on time within budget. Differentiate between waterfall model and the agile model of software development. Waterfall model follows a strict line of why is prototyping useful in SDLC? Prototyping allows users to allows customers to see how the end product will look like. What are the 4 quadrants activities of the spiral model? I don't know this one. I'll just leave it blank. Unit 2. The primary purpose is to state all the objectives and goals stated clearly before developers start building the project. Explain the difference between functional and non-functional requirements. Functional requirements are those What is the fundamental difference between coupling and cohesion? Coupling. It should be low. Coupling is when the modules are deeply connected to one another. Cohesion. It should be high. Cohesion states that one piece of code should perform only one function and it should perform the function exceptionally well. What does refactoring means? Refactoring means that that we change the internal code without actually changing the external code. Interface. White box testing is when we know how white box testing is when we know how the internal code works. And do the testing. The testing. Black box testing is when we do not have the knowledge of the internal code, but we test the input and output. What is regression testing? Regression testing is when changes to code affected any older features. That's it. Explain the difference between unit testing. Okay. Unit testing is performed to check a single module integration testing is performed noticed how good is. Name to automate. Okay. JUnit. Used for Java code testing. Selenium. Used for web-based testing. Unit 4. Kokomo. Kokomo stands for constructive cost model. It is used to estimate the number of developers required the time taken, cost to be paid, cost for a project. Difference between reverse engineering and re-engineering. Reverse engineering take an existing project, existing piece of code and look at its and trace back its architecture and budget. Re-engineering when we take an existing piece of code and modify it to it with modern software Configuration management, I forgot this. So software maintenance. Software maintenance. Preventative. Adaptive. And I know only two. Determine objectives, identify goals, constraints, and alternatives. And identify and resolve risks. This is the most crucial part of the spiral model. Risk analysis, development and testing, engineering the next version of the software, plan the next phase, review the results and plan the next iteration. Unit 2 SRS. It serves as a formal contract between the client and the developers, ensuring everyone is on the same page regarding what needs to be built. 2 functional versus non-functional. Think of function, what the system does, and non-functional, how well the system does it. Coupling, cohesion and refactoring. Alright, unit 3. Testing types. Second, configuration management. Okay, this one I have not answered. Why is configuration management important? SCM. It tracks and controls changes to the software's source code, documentation, and environment. Without it, developers might override each other's work, lose track of different versions, example v1.0 versus v2.0, or deploy wrong code to production. For software maintenance type, you perfectly named corrective and preventive. Okay, I forgot these two, corrective and preventive. Okay, so this is it. I would like to close it here. I will practice long questions some other time. Thank you.